Now, let me recapitulate. Our aim is to find out the optimal cross section of this particular single point cutting tool, subject to the condition that there is no mechanical breakage while doing that machining. Now, here if we just try to see, if we try to analyze the nature of these two objectives, so we can find out that our aim is to find out that particular cross section of the cutting tool which corresponds to the minimum weight of the cutting tool, and at the same time the developed stress should be less than equal to the permissible the value of the developed stress. Now, these two objectives actually are such that they are conflicting in nature. Now, for example, say if I just go for the more weight of this particular cutting tool, the developed stress, the developed bending stress will be less and vice versa. That means, if I go for the lighter weight for this particular cutting tool, there is a possibility that the developed stress will be more and there could be some failure in terms of the developed stress. So, our aim is to minimize both the weight of the cutting tool and at the same time the developed bending stress. However, these two objectives are conflicting and they are fighting with each other. Now, that means, if the weight of the cutting tool increases, the developed stress is going to decrease vice versa and vice versa, and using this particular the information I can formulate as a two objective optimization problem as follows. Now, our aim is to minimize the weight of this particular the cutting tool, and that is nothing but f 1 is a function of b and h, that is the width and the height of the cutting tool, and that is nothing but 157 b h. This I have already formulated. Now, the second objective is nothing but minimize another function of b comma h is nothing but 300 divided by b h square multiplied by 1 divided by 10 raised to the power 6, just to express this particular developed stress in MPa, that is nothing but Newton per millimeter square. Now, here our aim is to minimize the weight of the cutting tool and to minimize the developed stress like this, and these are nothing but the range for the design variables. Now, let us see how to tackle this type of problem having two objectives and where both the objectives are conflicting in nature, and our aim is to minimize both the objectives. So, let us see how to find out the optimal solution or how to find out the Pareto optimal front top solution. Now, I am just going to discuss a particular method that is called the distance based Pareto GA. The working principle of this distance based Pareto GA, that is DPGA, I have discussed in detail, and now I am just going to use the principle of this particular DPGA to solve these two objective optimization problem. The principle, as I told, I have discussed in much more details, but let us see how to solve this particular the real world problem using the principle of the DPGA. Now, here if we remember, we start with actually a population of solution, and these solutions are generated at random. Supposing that the total population size is denoted by n, and this particular population is divided into two subpopulation, that is n 1 and n 2. So, n 1 is nothing but going to contain all the solutions on which the GA operators are going to operate, and n 2 is another subpopulation that contains all the non-dominated solution, with the help of which we can find out what should be the Pareto optimal front top solution. Now, the way it works, So, as I told that the whole population is generated at random and the design variables should lie within their respective ranges. Now, we know the range for this B and H, and the first solution is selected at random, supposing that B is equal to 0.010 and H is nothing but 0.015. Now, this B and H, if I just substitute in the value of this particular the expression for H 1, this F 1 and F 2. So, I will be getting the numerical value for this particular F 1 and the numerical value for this particular the F 2. And once I have got the numerical value for this particular F 1 and F 2. So, F 1 is coming to be equal to 0.236, F 2 is 133.3, and the D minimum we do not assign anything here, and we assign some random fitness for these particular the solution, that is the first solution, and let me assign that this is 100.00. So, this is the random fitness we assign to this particular the solution 1, and we put the first solution in the non-dominated set. So, this E k indicates actually the non-dominated set. The first solution I am going to put in the non-dominated set. Now, once we have done it, next we go for the second solution, and once again B and H, those values are selected at random lying within their respective ranges. Now, using the expression for these two objectives, we calculate this F 1 and F 2, and once we have got this particular F 1 and F 2, let us discuss how to determine this particular D min and how to find out the modified fitness and how to take the decision whether the second solution will enter the non-dominated front or not. So, how to take all such situations I am going to discuss. Now, if I compare the values of the objective function, that means, if I compare this F 1 corresponding to the first and the second. So, these two things if I compare corresponding to the second solution. So, F 1 is more compared to the first solution, that means, so corresponding to the second solution. So, this 0.283 is a dominated solution, that is the worst solution compared to this 0.236, because this is a minimization problem. Similarly, if I compare the F 2 values corresponding to the first solution and the second solution, then the second solution in terms of x 2 F 2 is found to be worse compared to this F 2 in the first solution. That means, 277.8 is higher compared to 133.3, but as I told, our aim is to minimize both the objectives F 1 and F 2, but unfortunately corresponding to the second solution, both F 1 and F 2 are found to be worse compared to the respective values of F 1 and F 2 for the first solution. That means, the second solution is a dominated one, second solution is a dominated one corresponding to the first solution with respect to both F 1 and F 2. That means, this second solution is not going to enter the non-dominated set. That means, second is not going to enter. So, the non-dominated set will contain only solution 1. Now, how to determine this D minimum and how to calculate this particular the fitness. So, that I am going to discuss. Now, let us see how to find out that. Now, to find out that, we take the help of this particular calculation of the Euclidean distance between k and x. So, k indicates actually the non-dominated solution and x is nothing but the second solution, which I am going to take, for which I am going to take the decision whether it will enter the non-dominated set or not. Now, what we do is, so in terms of f 1 and in terms of f 2, so I am just going to find out this particular the Euclidean distance. Now, 0.236 is nothing but the value of f 1 corresponding to the non-dominated solution, and 0.283 is the value of f 1 corresponding to the second solution. So, we try to find out this particular the numerical value for this. Similarly, this 133.3 is nothing but the value of the f 2 with respect to the non-dominated solution, that is the first solution, and this 277.8 is nothing but the value of f 2 with respect to the second solution. So, using this particular expression I can find out the Euclidean distance between the non-dominated solution, that is k, and the second solution, that is nothing but x. So, I can find out what is this particular the dkx. Now, here I have got only one Euclidean distance value. The reason is I have got till now I have got only one non-dominated solution, that is k, and that is why there is only one Euclidean distance value, and as there is only one, that is nothing but d minimum, and d minimum is 1.102. Now, as solution 2 is dominated by solution 1, that is the elite solution in terms of both the objectives. So, this particular solution 2 is not selected in the elite set, and its fitness is calculated as follows according to the rule of DPGA, that is the maximum between 0, the fitness of the non-dominated solution, that is 100.00 minus this d minimum 1.102, that is nothing but 98.89. That means, using this I can find out like what should be the value for this particular the calculated fitness, that is 98.89. And now, I am just going to concentrate on the third solution. Now, the third solution, the b and h values are selected at random, that is b equals to 0.100 and h is nothing but 0.080, and the value of the objective function, that is f 1 is calculated like this and f 2 is calculated like this. Now, let us see how to take the decision whether the third solution will enter the elite set or not, and how to calculate this particular fitness and how to find out this d minimum. Now, to take that particular decision, I will have to concentrate on the non-dominated set. That means, I will have to compare this particular value of f 1 with this and this particular value of f 2 with this. Now, if I compare the value of f 1 corresponding to the first non-dominated solution, that is 0.236, and corresponding to the third, it is 12.576. Now, if I compare these two, definitely this is higher compared to this 0.236, and this is a minimization problem. So, this is not a very good solution. So, the solution 3 is worse compared to the non-dominated solution in terms of f 1. Now, let me compare in terms of f 2. Now, if I compare, so this 133.3 with 0.037, and as this is a minimization problem. So, in terms of f 2, the solution 3 is better compared to the solution 1, that is the non-dominated solution, because this is a lower value compared to 133.3. That means, solution 3 is a non-dominated solution with respect to f 2, at least one objective function, but not with respect to f 1. Now, as it is found to be better compared to the already found elite solution in terms of at least one objective function that is copied in the elite set. So, the solution 3 is copied in the elite set. So, the elite set will contain 1, 3, and once you have selected here, let us see how to find out this D minimum and the calculated fitness. Now, to find out that, actually what I will have to do is, I will have to calculate for the third solution the Euclidean distance d k x is nothing but the Euclidean distance between the kth non-dominated solution and the third solution, that is capital X, and this is nothing but square root 0.236, that is the value of f 1 corresponding to the non-dominated one, the value of f 1 corresponding to the non-dominated one, and 12.576 is the value of f 1 corresponding to the third solution. Next, 130.3 is the value of f 2 corresponding to the non-dominated solution. Then 0.037 is the value of f 2 with respect to the third solution, and I can find out the Euclidean distance values. And as there is only one Euclidean distance value till now, so this is nothing but D minimum. Now, as the solution 3 is a non-dominated with respect to f 2, with respect to at least f 2 in comparison with the elite set. So, this will be included in the elite set, that means, solution 3 will be included in the elite set, and its fitness will be calculated as the 100.00, that is the value of the elite set, the fitness value of the elite set, plus this D minimum, that is 50.297, and that is nothing but 152.297. So, this is actually the calculated fitness for this particular the third solution. And once you have got the fitness for this particular the third solution, now I am in a position to write down this particular fitness for the third solution, that is 152.297, and the solution 3 is going to enter. So, this particular the non-dominated set. The same procedure I will have to follow for the other solution of the population. So, similarly, I go for the 4th, 5th, 6th and so on for the whole population, and iteratively we can find out that a large number of solutions are going to enter this non-dominated front, and as I told that the size of the non-dominated front is going to increase, and consequently, the size of this n 1 on which the GA operators are going to operate is going to be reduced. Now, on n 1 the GA operators are going to work just to bring diversification in the population, and on n 2 subpopulation, that means, n is nothing but n 1 plus n 2. So, on n 1 the GA operators are working, and n 2 indicates the size of or the subpopulation of your the non-dominated set. Now, this particular non-dominated set is going to determine what should be the Pareto optimal front of solution. And if we follow this principle, so there is a possibility that this DPGA can find out ultimately the non-dominated set of solution, and if you just plot them, like if I plot f 1 versus f 2. So, this is f 1, this is f 2, and our aim is to minimize both f 1 f 2, and if I just concentrate on this non-dominated front solution, and if I plot, so there is a possibility that I will be getting this type of Pareto optimal front of solution. So, this possibility is there, and using this DPGA, so I can find out this Pareto optimal front of solution for the single point cutting tool. So, this is the way actually we will have to use the principle of DPGA to find out like what should be the optimal values for this particular the width of the cutting tool and the depth of the cutting tool, so that it can ensure the minimum weight and the minimum developed stress. So, this is the way actually we can find out the Pareto optimal front of solution using the principle of your DPGA, that is distance based Pareto GA. Now, I am just going to discuss the principle of another efficient tool to obtain the Pareto optimal front of solution, and the name of the algorithm is nothing but your NSGA, that is non dominated sorting genetic algorithm. The second version NSGA 2 I am just going to discuss. Now, the principle I have already discussed, and now I am just going to see using the principle of this NSGA 2 how to find out the Pareto optimal front of solution. Now, for this NSGA 2, as I have already discussed, that we are going to use the principle of the crowding distance just to ensure the diversity of the population of solution, and at the same time to ensure the selection pressure, we take the help of some sort of reproduction scheme like say the tournament selection. And using this the tournament selection as a reproduction scheme and the crowding distance, the concept, just to find out the diversification, we try to keep a proper balance between the population diversity and the selection pressure. And using the principle of this crossover and mutation, we try to bring some the new solutions in the population. And if I follow this particular principle, there is a possibility that I will be getting the Pareto optimal front of solution. Now, here along this I am just going to plot the mass, that is nothing but F1, and the developed stress is nothing but F2, and our aim is to minimize both F1 and F2. But the fact is, if F1 increases, then F2 is going to be reduced and vice versa. So, that is the fact, that means these two objectives are going to conflict each other, and there is a possibility if I use this NSGA 2 through a large number of iteration. So, gradually it will try to find out this type of Pareto optimal front of solution. Now, here on this Pareto optimal front of solution, actually we have got a number of possible optimal solution. Now, the user can select any one out of these large number of solutions lying in the Pareto optimal front according to his choice. Now, here on this particular table, so we are going to show some of the values of the design variables corresponding to the optimal solution. For example, if you see the solution 1, B is 0.005, H is 0.2, mass is found to be equal to 0.157 and the developed stress is 150 MPa Newton per millimeter square. Now, here if I see, so this corresponding to this solution 1 might be, this is the point, this is the solution corresponding to the solution 1. So, this is one extreme solution lying within the feasible range for this on this Pareto optimal front. Now, another feasible, the borderline solution could be this, and might be this corresponds to the second solution here, that is 0.2, H equals to 0.1, mass is 31.4 and the developed stress is 0.15. So, this could be second solution. Then comes solution 3, B is 0.005, H is 0.094, mass is 0.739 and the stress is 6.79. The 6.79 it could be here, might be I am here. So, this is your 0.3. Next comes the solution 4, that is B is 0.0106, H is 0.1, mass is 1.66 and the stress is nothing but 2.83. So, stress is 2.83. So, might be here. So, this could be your 0.4. Similarly, we have got other points. Now, the user can choose any one according to his choice, and all the solutions are optimal solution. with respect to the different weightage or different weights on the two objective functions like f 1 and f 2. Now, out of all the possible optimal solution, the user can select any one. So, this is the way actually we can find out the Pareto optimal front of solution. That means, different optimal solution for this particular the single point cutting tool, and as I told several times, once we have got the optimal values for this particular B and H, the length of the cutting tool is kept fixed. So, I can find out what should be the optimal design or the several optimal design. Now, I can choose any one depending on the choice, and this is the way actually we can find out the optimal multiple optimal solution for this type of the two objective optimization problem. That means, using this the different algorithms like some traditional optimization algorithm and some non-traditional optimization algorithm, I can find out the optimal solution for the practical problem, that is the optimal cross section or the optimal design for this particular the single point turning tool. And as I told, so this problem, the same problem has been tackled using the principle of single objective optimization and multi objective, that is two objective optimization. So, the optimization algorithm whose working principle we have discussed in much more detail can be used to solve the real world optimization problem in a very efficient way. Thank you.